Okay, good morning. I'm Risto Miikkulainen, Sentient Technologies and UT Austin. And I'm going to talk about how evolutionary computation is the next deep learning. I believe that, and many other people who've been working in this field believe that, and I'll try to convince you of that too. So, we have had lots of successes with AI recent years, most of them based on deep learning. Some reinforcement learning successes as well. And that is all good. Deep learning in particular has lots of applications in language and vision, speech understanding, and so on. But in all of those cases, there's something in common, that we are trying to do what we already know how to do well, how humans know how to do well. And we come up with training sets, data sets, where there's inputs and there's targets that are the correct outputs. So we're trying to model and we're trying to predict. And we believe that there's another kind of AI that's emerging now, and that is the creative AI, machine creativity, where you are creating solutions that don't already exist, solutions that are better than humans can come up with, or even solutions that humans can't even conceive, that they are so novel. And that's where evolutionary computation comes in. That's where machine creativity comes in. Like deep learning, these techniques, this machine creativity, is based on massively parallel and massively distributed computation. That's what makes it work. Some of the ideas have existed already for decades, just like they have in deep learning. But now, with 1,000,000 times more compute than we had originally, they now work. So that's the promise. The creativity is the next big idea in AI. So let's think about where this is coming from. How do human designers, developers create new solutions? The typical approach is that you start with something that already exists. It might be a very simple solution to your problem. Like here we have on top, we have a web page design. It consists of a number of elements and components and values. And you start with a web page that already exists, and you try to improve it by changing it. Changing some of the elements, changing some of the values. You see how well they work, and then you keep those ideas that work and iterate in this loop. Same thing with deep learning network design, which is on the right here. You start with something known, maybe an architecture for another domain, and then you try to adapt it to your domain by making these changes and iterating in this loop. Until you can find some better designs, you might start with a completely different starting point, or maybe just decide that it's good enough and deploy it. So that's a human creative process in many engineering tasks. And it turns out that that's actually the same process as deep learning and other techniques, reinforcement learning, are using. You start with a solution, a single solution, and hopefully that it's already a good one. It makes the task a little easier. And then you continually improve it through step by step. In deep learning, we know that you can use gradients. You can calculate the gradients. They come from a dating set. You'd use your targets to figure out where the actual correct solutions are. And that's your direction, how to climb the next hill. All of this is hill climbing. Human problem solving, as well as deep learning, reinforcement learning, is hill climbing. Gradient descent or gradient ascent. So you get gradients from those targets. In reinforcement learning, it's a little trickier because there's no target the same way as there are targets in deep learning. But you feel your way around. You have a solution, you look around neighboring solutions, and that way you try to estimate where the gradient might be. And this way you climb the nearest hill. And if it doesn't work, you may have to do a restart and climb another hill that's nearby. So in this sense, machine learning captures what humans are already doing in creative domains. And they've been successful in this gradient following and this feeling of the gradient in terms of image processing, natural language processing, even game playing. But if we really want to be creative and attack problems where creativity is central, we have to do better. The landscape usually does not look that nice as it was in those images. It looks something like this. Different designs can be very different, and they all perform to some degree well, and it's very hard to find out where the best creations are. So that's the first problem, that space is deceptive. You have to go down before you go up. And the current methods, gradient descent, reinforcement learning, are not really good at that. The space can be very large in that there's many, many states to explore, And even multiple restarts don't really help there because there's just too many of those states where you could be. And also it can be very high dimensional. Not 10, 15 dimensions as usually we have in these domains, but maybe you have to optimize thousands or millions of variables at once in order to find that optimum. So those are big challenges in machine creativity. And I'd like to propose that we have a solution already. It's been around since the 70s, and now with the big compute we can make it work. And that is evolutionary computation, evolutionary optimization. Why it works is because it's population-based search. Instead of starting from a single point and expanding out and trying to follow a gradient, climb the nearest hill, you have multiple solutions. You have an entire population that you spread out throughout the space. They represent very different solutions to the same problem, and that way you cover much of that search space. And then you do parallel search. From each of those solutions, you look whether you can improve them. And there are also operators that allow you to cross over solutions and make large jumps, so you're not limited to local search either. And that's why this works in this kind of very challenging spaces. So there are some examples and indications, experiments that show that it might actually scale up the way we want it to scale up. So first, let's look at large search spaces. As a demonstration, some of my colleagues at Sentient, Babak Hoxha and Hormuz Sharzad, tried evolution on a multiplexer problem, where you have to use a bunch of bits to decide which one of the output bits to output. And that's a multiplexer. And it can be designed by just doing circuit design, but as a search problem, it's really hard. You have to search for rules that tell you how exactly the multiplexer works. So if you have, for instance, a 70-bit multiplexer, that means your search space is 2 to the 2 to the 70th. And that looks kind of compact, but if you really write it out as a number, how many states you have, and print it out in 10-point font, it will take light 95 years from the beginning of that number to the end of the number. That's how large the search space is. And you still can find solutions in it. Evolution can. And the reason is that it finds blocks, it finds schemas, small snippets that together work well, and then it recombines those into larger solutions. And this way you can eventually construct the entire multiplexer from those components that you find. So you search only a tiny, tiny fraction of that space, but find those things that work quickly and build up from there. Multiple variables, the second challenge. Kalyan Moideb at MSU has an experiment where they were optimizing a metal alloy production recipe. And that turned out to be a very high-dimensional problem because you have a whole process and multiple variables over time. And he kept solving it and kept making it more and more refined and fine-grained, and eventually had 1 billion variables that had to be optimized at once. You had to find the right value for 1 billion variables to find an optimum, and that was possible. It turned out to be successful. So we actually have an experiment that scales up to that level. A large number of variables can be solved. And the third one was the deception one, the very rugged landscape. And there's a reason why evolution is a very good fit for such landscapes. And that is that we don't have to optimize just a single objective. We don't have to climb one-dimensional hill, if you will, but we can have multiple objectives, typically performance and cost. And once we have multiple objectives, you can make progress in one direction if you can't make progress in another. And this way you can find your way around the hills. And there's lots of recent research in evolutionary computation trying to zoom into that property. For instance, novelty search. You make a secondary objective novelty. So not only you're optimizing the performance, but you're also trying to find new things, surprising, novel things. And you reward those that are different from things you already know and have. And therefore, you're building up stepping stones. And when you recombine stepping stones, you can discover something that's hard to discover other ways. There are many examples of that in image design and physical design and generally problem solving. All right, so this is then the argument that we come up with from that introduction, that evolution is the next deep learning. It's based on a computational power that now exists and we can utilize to take advantage of this population-based search. And we can use it to solve very hard problems in science as well as in AI. For instance, designing those architectures for the deep learning networks. That's one example I'm going to talk about in a minute. And there are also breakthrough applications that are ready now. And I'm going to talk about two. One that we build at Sentient, which is the website optimization application. Sentient is sent. You actually design websites automatically so that they convert casual users to paying customers as often as possible. And also I'm going to show another application which is much bigger potentially in the future, but it's future work. That's optimizing agriculture using this approach. All right, but let's first dive into a little bit to what evolutionary optimization is, because you may not be familiar with it and how it works. So in evolution, we have a population, like I said, and it's a population of encodings. That is some kind of a string structure or a tree structure that represents a DNA. And each individual is specified by its DNA. That's your population. Then you decode those DNA structures into your phenotype, which is the structure that you then deploy, like a neural network in this case. You put the neural network in the environment and see how well it performs. That's one number that comes back. It's a single objective function. Then there's one number, and that's how well it performs. That becomes the fitness of the individual, and it inherits the DNA inherits that fitness. So you have to test each of your population members, decode them, and test them in the environment in order to get the fitness. And now you can run evolution. Survival of the fittest. You throw away the bad ones, and you keep the good ones, and they become parents. Like here, you take their DNA encoding and you cross it over. And that's inspiration from biology. You can have multiple crossover points. You can randomly flip bits based on randomly choose them among the parents. But the idea is that you take the DNA from the two parents and you form a recombination. Therefore, you can get an offspring that hopefully combines. Some of the offspring combines the good traits of both parents. That's what allows you to solve a to the 70th multiplexer, because you are combining those partial solutions, and sometimes some of those offspring combine the good parts. You also have mutation, because you do want to be able to create new building blocks as well. And that's how evolution progresses. It's a search mechanism. You throw away the bad ones, keep the good ones, replace the bad ones with the offspring, and iterate. And that allows you to cover much of the search space. Let's see how that happens. Here's an illustration of the website optimization problem, and we'll show how the search space actually tells you how evolution search works. So here's a general setup for the Ascend problem, optimizing web page designs. There's a web page here, and a developer, a human, has gone in and decided that, okay, here are the things I can change, and here are the values that they can take. Like, what is the color of the button? What is the background image? What kind of text do I have? And each one of those elements has a number of different choices. And this search space grows very quickly. In this case, in just a few elements and few values each, we already have 10,000 different choices. Typically, in a web page design, we look at 100,000, maybe million of different choices. And that's what we try to evaluate. We try to find good ones in that space. So initially, we initialize the space with designs that humans come up with, or maybe we randomly mutate them to come up with a population. And that should cover much of the search space. And generally, that's relatively easy to do. Your solutions are sprinkled around the space. We evaluate them, and in this case, the evaluation result is illustrated by the size of the dot. How big the dot is illustrates how well it performs. How many users on average convert and click on the button on that site. And then we throw away the bad ones and select the good ones to be parents. So here are the two largest dots. They each represent a different web page design. And then we cross them over and form an offspring. And here, indeed, you can see that some of the elements come from one parent, other parts come from another. So it's truly a crossover, an offspring of those parents, parent designs. And now we populate the space with offspring. We might keep the parents around, but we replace all the bad designs with offspring of those good parents. And you can already see that there's more large dots there, many large dots, and also you don't cover the entire space anymore. You're already trying to zoom into those parts where there are good designs. And over several generations, this process accentuates and gradually zooms in where the really good designs are. And now you have a refinement phase, your evolution discovers the actual peaks around those areas. And there may be multiple of them. It doesn't have to be one design. Hopefully we discover the best design, but there may be alternatives as well, because it's a population. And that's how you increase convergence in websites. Let's take a look at an actual case study of sentient assent to make this more concrete. This was more of a description in a conceptual sense, how evolution works. Let's see how it looks like on the website. So here's an actual case study, Above Media. Their website tries to connect users with educational programs. And we were optimizing just that widget. Everything else was still under their control, but we were optimizing the design of this widget, including the colors and the texts and some of the layout elements. And you might think that that's a small thing, but it's surprising how big an effect it can have. So let's see what happens. Over time, we generate an initial population of designs for that widgets, and then evaluate each one of them and run evolution from there on. And here in the plot on the left, you see orange is the control. That's the design that we see on the right. And then above it, we have two lines. The top one is the best performing candidate so far that we found at this point in evolution. And we also have a confidence bound, because we have to test each candidate with number of users. And the more users you have, the more confident you are in the convergence rate. But it's a limited resource, so we have a confidence bound. We also have an average of all the tests that we've done. With all the candidates at this point, what is our average conversion rate? And when I click, you see a little movie that progresses over time, and you see these two lines rising above the orange line. And on the right, you see some of the designs that evolution comes up with. And you can see that they are, some of them, pretty different from the control. So here we go. The bands get narrower, but then we have a new generation, which is a peak on the bands because they are new candidates we haven't seen before. And on the right, you saw very quickly a movie that went through a bunch of these designs. Let's see if I could play it again. So there you go. There are some of the designs, and you can very quickly see that the designs look different from those that the humans came up with. In particular, they're much more engaging. They're actually kind of garish in some cases. And the humans who designed this website, they called this evolution system the ugly widget generator, because to them, they look ugly. They go against their nature. I don't want to use colors like this, but turns out you should. They actually work. They draw attention to that widget. But that's not the only thing. The text there is much more active. It's choose a program, find my program. And little things like that make a difference. And as a matter of fact, they make a big difference. Just let's compare the two. I mean, which one would you be more likely to click on? You're actually drawn to the one on the right, and it is effective. And as a result, 45% more conversions happens with that web design on the right. And this is already starting from a point where humans did the original work. So there's still that much to be gained. And what's remarkable is that we've been able to do this over and over and over again. Ascend is a product, we sell it, Sentient sells it, and it's been applied to many different industries, many different levels of traffic, sizes of web pages, search spaces, and it quite reliably finds lift beyond human design. And often it finds it by discovering these interactions that miss human judgment, and also these choices that are somewhat difficult for humans to appreciate. But users vote with their feet, or at least their finger when they click. Okay, so that was Abu Media. That was an example of an application of evolutionary optimization that's already out there as a commercial application that people pay money for. And they actually gain much more than they pay for. That makes sense. This kind of conversion rate improvements, like 45%, is huge. It makes a big difference. It brings in a lot of revenue. All right, now let's look at a little bit more scientific topic, academic topic, but also very illustrative, designing deep learning architectures. So here are three architectures I just pulled from the literature. You may recognize some of them. The one on the left is an image recognition architecture. The one on the right is image captioning. for different tasks, you use different kinds of architectures. And they become really complicated over the last couple of years. Not just multiple layers, but repetitive substructures and different kinds of layers. Many hyperparameters. How do you actually optimize it? How do you find the right architecture? There must be some principles of organization, and that's what human ingenuity can try to come up with. But still, you need to cover enough of the search space to verify that you found some of the good ones there. So what would you do? Well, turns out evolution is a really good match with this problem. The crossover operator manages to discover structure and recombine structure. So it's a very good match with that. And also because it's population-based search, you can cover much of the search space. So that's the promise, that's the motivation of trying evolution on this problem. Let's look at two examples how you could do it. And they appear in two different levels. So the first one is at the level of individual nodes. So if you know LSTM networks, the recurrent memory networks, there is a node structure that has a memory cell and a bunch of gates and some paths through it that was proposed in 95 or something like that by Hochreiter and Schmidhuber. And it's been stable for about 25 years. That same architecture lasted that long. And people even wrote papers, Schmidhuber wrote papers suggesting that the variations that had been proposed did not make much of a difference. This vanilla LSTM architecture is what works. So let's do the following example. Let's use that architecture perhaps as a starting point, but define a search space around it. So you can modify the design of the LSTM. You can add more pathways, more memory cells, more gates, and let's see if we can come up with something that works better. But only evolve the node. And you just put that node then into a structure like a layer, and then maybe 2 layers, and that's your network that gets evaluated. And that's what this illustration here suggests. And we also use tree encoding for the node, because that's easy to evolve using genetic programming, a particular powerful set of evolutionary technology. All right, and then apply it to language modeling, say, the standard benchmark task for sequence processing. You have a large corpus of tasks, like Penn Tree Bank, and you try to predict what the next word is in that sequence. All right, so here are some results. Indeed, evolution came up with much more complicated architectures. The standard is in the left, the evolved cell is on the right. There are more memory cells, not just one, and there are multiple paths through the node, and many of them are nonlinear. And some of the inputs are used multiple times in those different paths. So this is complexity that would be very hard for humans to discover, but it actually makes a difference. The cell on the right performs 15% better in perplexity than the original LSTM cell. Now, you might think that it might be just the complexity that you added and that helps. Well, we tried this on another domain. We took the evolved cell and put it into a music prediction task. Piano scroll, and you predict what the next note will be. And it did not perform any better than the standard LSTM in that task. But then we evolved again from scratch for music and found that we did improve on LSTM. A different node structure emerged. So there is actually meaning to this. You discover complexity that matters. Not just complexity, but the right kind of complexity. And evolution can discover that and encode it in a structure that then works in the domain that you have. So we have a demo on this. You can actually type some piano notes and hear how the LSTM would continue it, inspired by your riff. So that was the node level evolution. Let's look at higher level, where you evolve entire architectures. And that means the topology of the network consisting of multiple layers, as well as building blocks. So we already have a separate evolution for building blocks, combining a smaller number of layers into a block that can then be repeated as part of the larger architecture. And we apply that. We can apply it to just a single task, but we can also apply it to multiple tasks at once, coming up with a network architecture that, for instance, given an image, might identify or label the object in the middle, or it might give you a caption that describes the image. And maybe a third task might be describe the relationships of the objects in the image. So they are related tasks, all based on the same input, but different outputs now. And why would you want to do it? Well, this is the idea of multitasking, and it's been around again since the 90s. And the idea is that you combine gradients from multiple tasks, and therefore the internal representations of the network become more general. And they become more powerful in that they have to support multiple tasks. They also generalize better in each of those tasks. And that's the promise. Each task, performance is better in each task because you get help from those others. Now the big question is, well, how do you actually combine multiple tasks? And that's where evolution comes in, or architecture search. You find an architecture that optimally combines the multiple tasks. It could be more linear architecture, where parallel, or something where the tasks are at different level, like in this image. That's for evolution to discover. So, as I said, we evolve modules and we evolve topologies. And the reason is that it might be a good idea to evolve a separate topology for each task and then tie them together by having the same set of modules participate in those topologies. So each module here is represented by a different color, and the modules with the same color are the same. And their weights are constrained to be the same. So the different topologies are constructed from the same components, and those components are trained in all the different tasks. That's how the tasks tie together. That's how you get benefit from multiple tasks. And here's an array of different solutions that emerged. Actually, I need to show what the task is. The task is here on top right. It's omniglot. It is recognizing characters from multiple alphabets at once. So you have to recognize that this is an alpha in Greek, or this is a B in Latin script, and there's Hebrew and Cyrillic and Korean. And each one of those tasks has very little training data, but there's 50 of them. And here's then the structure of networks that evolves. You start with a very simple structure, basically the linear array, and that works for some of the scripts. But the more complicated scripts actually receive more complex architectures. Evolution discovers more complex architectures for them. Not only that, if you have two scripts that look somewhat similar, like there are a couple of scripts that have a prominent horizontal line, I think Sanskrit may be one of them, then you get similar topologies for those two scripts. So there's again systematicity that's discovered. And also if you run this multiple times for the same script, you get similar architectures over multiple different independent runs. So again, evolution discovers principles and encodes it into these architectures. But also, I mentioned that there's very little data in each task, and that's crucial. That's important, because now you can use 49 other scripts or alphabets to improve your learning for the alphabet that you're currently interested in. So this is where we got a huge improvement over state of the art. 31% from just single task training that's currently in literature. That is a big improvement. And much of it has to do with combining multiple tasks, and especially combining their data requirements. We also achieved a state-of-the-art in another task, which is the Célébé multi-attribute face classification. So does this image, the person in this image, have sunglasses, or have a beard, or dark hair, blonde hair, smiling, different attributes that you are classifying these face pictures on. There we did get state-of-the-art, not quite 31%, but 0.75%. But this is also a task that has been beaten to death with lots of different approaches. We still achieved state-of-the-art by combining needs from those multiple classifications through architecture search into one neural network. And I need to mention that we do train the neural network, we don't evolve the weights. That's another approach where we could evolve also the weights instead of gradient descent. But here we are evolving the architecture and just then train the weights. So the important point here is that this can be used to apply to tasks that are related, and where little data might exist in one task. You could still use deep learning to learn it and do well. Okay, the last topic, the third example of changing the world with this technology, being creative, is surrogate optimization. And I think this is a new direction as well. Like machine creativity in general, surrogate optimization is a new application in the world. I see a lot of applications of it, but very little has been done yet. So in many domains, we already have data. and we can build a predictive model of that domain. Given some input, what is the output? For instance, predicting energy consumption over time, or stock market, or how plants grow. If I give this much water instead of that much, how much better is the plant going to be? We can build those models by just collecting the data, and the technology might be deep learning, it might be something else, but this data already exists in many domains. What's missing is actually changing the system, interventions in the system so we can do better. So with the energy consumption, for instance, how should we actually supply the energy so that we meet the demand better? In medical diagnosis, we know what treatments work, how a treatment works. We can build a predictive model. But what should the treatment look like? What's an optimal treatment? That's changing the input. That's changing the intervention. So that's what surrogate optimization is. You have an evaluation, which is now a model, and then you have an optimizer that creates candidates. And we use the model to evaluate the candidates, instead of having to do that in the real world. Like in Ascend, every web page was evaluated in the real world. With surrogate optimization, we don't show it in the real world. We show it to the model, and the model makes a prediction. This way, we can iterate very fast without much cost at all, and come up with good solutions before we ever deploy them. And there are lots of domains in the world that can benefit from this. And I think this is a great direction for future. And I want to talk about one pilot experiment that we've done in this area. And this is in agriculture. And that's kind of fascinating that something that big as an agriculture production could be amenable to these techniques. But there are lots of challenges in agriculture. We all know that the production of food and other agricultural products is costly, and there's not enough of it. But also the quality of agriculture has gone down. Since the 30s, and people study this, farmers and the market has optimized for size. So we got really large tomatoes, but they don't taste as good. They don't have as many nutrients. This is called dilution problem, that we optimize for size and volume and weight, but not for what the food is really about, which is taste and nutrients. Also, the plants that we need are often grown very far from where they are consumed. So if you go and pick up an apple from a grocery store, chances are it was actually picked from a tree 11 months ago, on average. And it's just a bowl of sugar. If we could instead grow it somewhere nearby, we could eat it right away and we'd get much better quality. So that's the challenge. How can we improve agriculture so that it becomes cheaper and better quality, and we don't have to distribute it as widely? That's the problem. We don't we don't know what the optimal recipes are for growing food. The farmer knows about his own patch of land and knows what to grow and how, but what if you could control everything? Light, nutrients, water, temperature. Could we do better? That's a potential solution. Let's build artificial environments, computer-controlled environments, where everything is controlled. And then we can try to optimize those recipes so that we get better quality. And we can build these environments where they are needed. We don't need to transport the food anymore. So this is the vision of Open Ag at MIT Media Lab, Caleb Harper's unit there. They're building these environments at different scales, 2 by 2 by 2 boxes, as well as container size, as we see here, and a whole farm of containers. And they can do that, but the problem is we don't know how to grow them, what the optimal recipes are. And that's where surrogate optimization comes in. We use the result from previous growth experiments to build a model, and then optimization to give you better recipes. So the pilot experiment focused on basil, and partly because it grows in 3 weeks, and we don't have to wait 200 years for a pecan tree to grow. And then we optimized the oil content, which is the taste and quality, and then the weight. And we could control light. This is a pilot experiment. We just used the type of light, the wavelength, how long the light period was, the day was, and then how much UV light was used. And then we had a container that was full of these experiments, 9 different trays at once. And that was enough. We could actually apply surrogate optimization and find some interesting things. So what did we find? Well, first we found a weight and taste trade-off. The dilution problem is real, and we could see it here. If we optimized for weight, we get results that were much lower on taste, on flavors, on those oils. And if we optimized for taste, then we got smaller basal plants. So we could see already this trade-off and demonstrate that it's real, and that's where dilution comes from. But we also discovered something we didn't already know. Nobody did. That we started with 18 hours of light and 6 hours of darkness, because the biologists in the team thought that plants need to sleep. Turns out evolution didn't care. It kept cranking up the daylight until it was 24 hours of light, no darkness at all. And basil loved it. We got much better results with 24 hours of light than we would have if we had just followed the biological instinct. And this was a big surprise to the biologists. And this is the promise. With evolution, with optimization, we can be creative. We can discover these solutions that don't already know, and they can be a start of a new industry, like in cyber agriculture. Okay, to conclude, I believe, and many others in the area, that the next generation of AI is creative. So instead of building models, we build systems that discover new solutions that don't already exist and we don't already know. And that can be done in engineering design, in systems optimization, behavior discovery, all kinds of domains, and including surrogate optimization, which takes it to the real world in a new scale. And evolutionary computation is a crucial ingredient. There are other approaches too, but evolution gives you the creativity. It gives you the novelty, the surprise, because it's parallel population-based search. And we can go all the way to create new industries. So if you're interested, there's a website address there. You can find out more and see many of the demos of the systems that I've talked about. And I believe we have 3 minutes for questions. Thank you. So are there any questions? Yeah. Do I use the mic? Yes, the mic is here, that's right. And there's another mic on that side.
It's pretty cool how you use the evolutionary theory to do the computation. My question is around what is the impact of such a complex model architecture, or on the performance of the prediction and the cost associated instead of doing by a single model or single architecture?
Yeah. So the 2 parts of that. So the final result of that neural architecture search is often a very complex neural network. And it turns out that's where the power is that comes from. But because evolution can work very well in multi-objective environments, it's a possible idea to add a minimization objective to evolution. And now you're discovering architectures that trade off performance and minimization. And we've done some early experiments along those lines. And we find that in the population, there's always a trade-off. You can find solutions that are really good, and they tend to be the most complex ones. But with a small price to pay, with lower performance, you can get networks that are much, much smaller, perform almost as well. And in the future, we plan to explore that more. And there are real objectives. Size, you have to fit it in memory. Execution time, you have to be very quick in answering. Even energy consumption. Those can become objectives, and we can minimize them. And another aspect of that is that it takes a long time to evaluate all the complex choices. And there's also technology that has to be developed with that. We can't afford to wait 5 days to train a single candidate. So we train it for 8 epochs only and predict where it will go. And that takes into account the shape of the learning curve, the structure that we're looking at. We can do better in prediction now than we could by just early stopping. And another aspect of that is, can this only be done with huge amount of compute? Well, the best results are based on hundreds of GPUs. But there's still room for creativity and ideas. And there are some examples where people have, like some of our experiments used 50 GPUs, and others used just 2. If you do weight inheritance, so you don't start from scratch every time, if you limit their search space in a clever manner, you can do much better even with less compute. And there's still room for ideas on how to do that right. But in the long run, this is an approach that can actually benefit from the compute that we have in the future. There are not many systems that can take advantage of 5,000 GPUs, tens of petaflops, but we can actually harness it in the future. Whatever ideas we have, we can scale them up, and that is a really good thing as well. Okay. Oh yeah, one more.
I just try to clarify the problem I missed. When you do your web design evolution, what's your fitness function?
Yes. So the fitness function is the performance of the network after it has been trained. Now, when we are evolving neural networks, that's what you're asking about.
Yeah, I just say, how do you evaluate this generation is better than last?
Yeah. So how is this generation better than the previous generation? You have to define how you evaluate your candidates. And in terms of neural network, we take each candidate, train it with the training set, test it with validation, and the performance on the validation set is our fitness for that candidate. And that allows us to decide which ones of the candidates are good and which ones are bad. But that's totally domain dependent. In Ascend, we deploy the page and let it run for several days, maybe a week, and we see what percentage of users convert. That becomes the fitness. And same in a design, you might actually implement the design in a CAD system and simulate it and see how well it performs. So there are many ways of doing that. A lot of them are very computationally extensive, and that's why the parallelization helps, because you can do the evaluation on different GPUs, on different CPUs, and that's how you get the benefit. Okay, I think are we out of time, or do we still have time? I don't quite know. There are a couple of questions. Maybe I take these two and then stop. Okay. And you can go with the other microphone.
I had actually two questions. When you say evolutionary algorithms, a long time ago in grad school, I studied about simulated annealing genetic algorithms.
Yes.
Are you still talking about the same ones, or has
yes,
there been progress in this field?
Very good question.
That's first question.
Okay.
Second question.
Okay, I'll try to remember that. All right.
Do you have open source stuff that we can go try out?
Yes. I think that was actually the length of my talk, so I still have 5-6 minutes for questions, so I'll be good. Right, so the open source first, because that was on top of my mind. So yes, there's actually some good packages that include many different evolutionary algorithms. ECJ, evolutionary computation in Java, is one such package. It includes contributions from many different groups. What we are doing, in particular, NEAT is one such package, and it's in a couple of different places, including University of Texas and Central Florida, and a couple of other versions of that. One thing that we are working on now is making more open source of the latest architecture certs available. We try to make something in conjunction with TensorFlow or something like that. So that's still to happen. But evolutionary algorithms you can certainly test already. And the first, the genetic algorithms of the past. Like most of these ideas in deep learning, the ideas originate from those times, from the 70s even, and there's been steady progress since then. But now there's a couple of new ideas that makes this different. And I, in particular, would like to point out the novelty search, which is a new idea that if you want to optimize something, you don't just steadfastly try to get improvement, but you let evolution handle multiple different ways of getting there. You reward something just because it's different from what you've seen. That's a new idea, and understanding why it works, making it work, identifying stepping stones that combine well, that's what we're still trying to work on. And there are still better new implementations of like genetic programming, languages that are now evolved, not just Lisp, but like Push, which is designed to do GP. So there are these advances that are new, that didn't exist back then, that make the approach much more powerful. And the third category, I think, is that techniques that make it run with enormous compute. So for instance, at Sentient, we have an easy star system developed together with MIT CSAIL, Una May Riley, that distributes the evolution to the point where at one point, we're running 2 million CPUs. Evolution was distributed across 2 million CPUs. And that adds a lot of power. And then you have to come up with techniques to take advantage of that. Like how do you pool the results? How do you asynchronously evaluate things? And so on. So that's all new. So indeed, there are lots of ideas since then, but also the scale-up requires some new work. I think that answered that. Okay.
So,
are we out of time? Oh, okay. Sorry about that. I thought we had until 11:55, but we're out of time, so thank you.